Hello, welcome to another lecture on exact solution to viscous flows. In this lecture, I am going to discuss the Hagen-Poiseuille flow. Hagen-Poiseuille flow. Hagen-Poiseuille flow is the developed flow in a circular pipe. In a circular pipe. So, the Hagen-Poiseuille equation are for the velocity along the axis of the pipe, that is u is z. That in the developed flow, it's a function of r only, and also the discharge as a function of some function of the pressure gradient. So, as a in terms of discharge in terms of the pressure gradient, and of course the radius, viscosity, etc. So for the flow through a pipe and developed flow, so thus this is the central line axis of the pipe, and this is the pipe wall on one side, and maybe after 180-degree, then there will be one more on the bottom, and I mark the x-axis like this, and y-axis the y-axis, and sorry, not y-axis but radius. So radius, okay. This is the axis, so I will have this z. So the axial direction is z, and this is the radius. And if you take a plane, like this, and then if you look from here, we can draw what is you can draw a circle. That view is a circle. The view is a circle, and this radius is this radius is the outer the radius of the pipe. That is R, capital R is the radius of the pipe, that can be marked here as this much is R, and at any point has a certain radius. So this distance will be area radius R. So the R varies from 0 to capital R. So, and this could be an XY plane also. X axis like this. So this is the Z axis, Y axis. So X axis could be drawn like this. X axis could be the positive X axis could be drawn like this, and this is Y axis. So the fluid flows through this pipe. At the entry, the fluid velocity is an average velocity. Average velocity is there at the entry, that is uniform average velocity. at the entry. And because of the wall and no slip conditions, because of the wall and stopping of the flow near the walls, there will be a displacement of fluid particles towards the center. And in the entry region, there will be some kind of movement of particles towards the axis or center of the pipe. So this velocity distribution changes something like this in this entry region, and it goes on changing till you get a velocity distribution at some point at some z some z value at some z value. You get a velocity distribution something like this. That velocity distribution, this velocity distribution does not change as the z increases. With increase of the z, this velocity distribution does not change. So this does not change. Such a velocity distribution is called the developed flow velocity distribution. So in this developed flow, this component of velocity is u z actually. This is u z component of velocity. U is z, that is dou by dou z of u z is equal to 0, or any dou by dou z is equal to 0. That is the condition for developed flow. Developed flow. So under this developed flow condition, and also the flow is laminar, okay, incompressible, three developed, and here I will write steady. So as far as the u theta is concerned, there is no the tangential component of velocity in the pipe. So we assume there is no tangential component of velocity at the inlet. So tangential component of velocity no. So this is also called sold. There is no inlet sold, no inlet sold. So u theta is 0. U theta is equal to 0. We are saying u theta is equal to 0, and that is the pipe is axis symmetric. So there is no the variation of flow property or flow parameters with theta in theta direction. In theta. Whereas in the radius direction there are variations. So a continuity equation is dou ur by dou r plus ur by r plus dou u theta by r dou theta plus dou uz by dou z is equal to 0. So in this, already we talked u theta is equal to 0. U theta is equal to 0. This is equal to 0. So and also for developed flow, this is equal to 0. For developed flow, dou uz by dou z is equal to 0. So this can be written as 1 by r dou by dou r of r u r. Plus dou uz by dou z equal to 0. This is equal to 0. So this is equal to 0. So dou by dou r of r u r is equal to 0. So r u r is a constant, or u r is equal to constant by r. And we know at r is equal to capital R, the velocity. So r is equal to capital R. the no slip condition gives ur is equal to 0. So ur is equal to 0. So ur is equal to 0 at capital R. So this constant, whatever this constant is equal to 0. That way, the ur is also equal to 0. This implies ur is also equal to 0. So you get ur is also, there is no radial velocity also in the developed condition. That is in the developed region. Whereas this region there will be a radial velocity, because there will be a radial velocity from outer radius to inner radius there will be. So in the developing region there is a ur, but in the developed region ur is equal to 0. So with these informations we can simplify the Navier-Stokes equation for the axial momentum, for the axial momentum equation. Actual momentum equation. If you take, that is dou u z by dou t plus ur dou u z by dou r plus u theta by r dou u z by dou theta plus uz dou uz by dou z is equal to minus 1 by dou p by dou z plus mu into dou squared uz by dou r squared plus 1 by r dou uz by dou r plus dou squared uz by r squared dou theta squared plus dou squared uz by dou z squared. So this is the z axial momentum equation. Out of this is 0 because steady, and we find that in developed flow ur is equal to 0 and u theta, there is no tangential component velocity in the whole pipe flow. So there is nothing, no swirl at the inlet, and this is 0 because of the developed flow, and this is there, this is there, this is there, and there is no variation in the theta direction. So this is equal to 0. So developed flow, there is no variation in the z direction, even for the first derivative, the second derivative also equal to 0. So, and we get the simplification in this form. Dou squared uz by dou r squared plus 1 by r dou uz by dou r is equal to 1 by rho dou p by dou z, and this mu can be taken to here at rho nu, sorry, mu can be taken to here, that becomes rho nu. The rho nu is basically mu, that is dynamic viscosity. So this kind of a relation, with this kind of a differential equation we get. In that also we know that uz is not a function of theta, is not changing with the z because of the developed flow, so it's a function of r only. uz is a function of r only. So this derivatives becomes total derivatives. So you can write d squared uz by dr squared plus 1 by r duz by dr is equal to 1 by mu dp by dz. So this is the ordinary differential equation, and ordinary differential equation for uz, and this dp by dz acts as the source. This is the non-homogeneous differential equation. So this is the non-homogeneous part, that is that drives or that produces the solution for uz. So values for uz, and our aim is to solve this differential equation. This is a simple differential equation. If you look at we can see that this is 1 by r d by dr of r into duz by dr. So that we can easily identify, because this is a product. So when this is when r is differentiated, it becomes 1, and that this term is that 1 by r will come here. When r is taken outside, r cancel, those two divided of this square. So this is equal to 1 by mu dp by dz. So it can be easily integrated. Okay, so this R goes to this side, so we have this to this side, so that is integrating once with respect to R, we get R duz by dr is equal to 1 by mu dp, 1 by mu dp by dz, dp by dz, R squared by 2 plus some C1, some constant C1. Or duz by dr is equal to dr is equal to 1 by mu dp by dz r by 2 plus c1 by r. So c1 by r. So this is the integrating once we get this kind of an equation, and let us see what is z1 then. So this is dou u z duz by dr, that is gradient of u z with respect to z with respect to radius, and we know at the center the velocity is maximum, and the duz by dr is equal to 0 at the center. So at r is equal to 0, duz by dr is equal to 0. At that condition we apply, so this has to be equal to 0, 1 by mu dp by dz into r is equal to 0. This becomes c1 by r. c1 by r. So limit r tending to 0, c1 by r is equal to 0. So basically this is a constant, and this is the 0. So something finite value for the ratio, so the limit should be on the form 0 by 0, then only this finite value 0 will be coming coming corresponding to duz by dr is equal to 0 at r equal to 0. So this is a ratio, denominator is equal to 0, the numerator also should be equal to 0, thereby it should have a form 0 by 0, and then the limiting value can be 0. So for to making the limiting value equal to 0, c1 is equal to 0. So c1 has to be equal to 0. So using this condition we get c1 is equal to 0. So our equation, you write duz by dr is equal to 1 by mu dp by dz r by 2 plus r by 2 plus the c1 is equal to 0. So c1 by r, say c1 by r is equal to 0. c1 is equal to 0 and c1 by r is equal to 0. So this is dz by r. Further integration we get uz is equal to 1 by u dp by dz 1 by 2 r squared by 2, that makes this 0, this 4 plus c2. C2 that's on c. And now that we know another condition is uz is equal to 0 at r becomes capital R. At this point uz is equal to 0. So uz is equal to 0. uz is equal to 0. So this is uz as a function of r and constant now. uz is a function of r and constant. So now we have uz at r is equal to r comma c1 is equal to 0. So 0 is equal to 1 by mu dp by dz 1 by 4 r squared plus c2. So this gives c2 is equal to minus 1 by 4 dp by dz 1 r squared 4. So substitute that here, we get uz is now a function of r only, that is this is positive and this is positive. These many things are constant, so that can be taken outside. 1 by 4 mu dt by dz minus is taken outside. So I'm having r squared minus r squared. So this is the velocity distribution, the developed flow in the radial direction. So this is the velocity variation, right? So we have taken the Navier-Stokes equation, expanded forming, and r theta is said, and that actual momentum equation is taken, and the simplifications are applied, thereby obtained an ordinary differential to have a solution, exact solution, and that is. And then I will now I will explain one more method for arriving at this u z is equal to r. That is somewhat simple compared to this. For for okay, I will explain that also. And for that we use the xy coordinates. So we look at this plane. This is a plane. We consider a plane like this in the cross sectional plane in the developed floor region. In the developed floor region, and write the governing equation in the xyz and that in the z direction. So we are using the Cartesian, and we write z component of moment. Z component. And that is dou uz by dou t plus u dou uz by dou x plus v dou uz by dou y plus w dou uz by dou z is equal to dou p by dou z plus u into dou squared u by dou x plus dou squared uz. Okay, uz only I am writing. It can be. It is normally written as w in the Cartesian coordinate system. But here I will write it as uz itself, so that we will have a match between those two, the previous equation and this equation. And this is 0, and the component of velocity is 0, y component of velocity is 0. This is developed because of that it is 0, and this is 0. So for this we get dou squared uz by dou x squared plus dou squared uz by dou y squared is equal to 1 by mu dp by dz. So this kind of an equation we get dp by dz. Okay, the pressure is varying in this direction only for the developed flow region. So we have dp by dz is equal to dou p by dou z is equal to dp by dz. So this is a kind of thing. And this is a Poisson's equation. It's a Poisson's equation. And the uz is the actual component of velocity which has to satisfy this Poisson's equation. And that also has to satisfy the boundary condition. The boundary condition for uz is equal to 0 on the wall. uz is equal to 0 everywhere on the wall. So everywhere on the wall of the cylinder. So the wall, the curve or outer or the wall of this wall of the pipe can be equation can be x squared plus y squared minus r squared is equal to 0. So this is the equation for this circle, which makes the surface of the pipe. So x squared plus y squared minus r squared is equal to 0. So at any point on the circle x squared plus y squared minus r squared is equal to 0. So if we take a function uz is equal to some a into x squared plus y squared minus r squared, then on the surface of the pipe, on the surface of the pipe, this will become equal to 0, and this uz can satisfy what is called the boundary condition. Boundary condition, the uz is equal to 0 on the surface. So if this is uz, we get dou squared uz by dou x squared is equal to 2a, and dou squared uz by dou y squared is also equal to 2a, and that you substitute here, you will get 4a is equal to 1 by mu dp by dz. or A is equal to 1 by mu 1 by 4 mu dp by dz. So that way uz is equal to uz is equal to A is 1 by 4 mu dp by dz into x squared plus y squared at any point is the radius squared r squared. So I will write it as capital R squared minus R squared, and there's a minus sign that is taken outside. So again we get uz from this also you get from this also you get uz as a function of R can be written as minus 1 by 4 mu dp by d is that capital R squared minus small r squared as the velocity distribution, which is this one, this same. So this derivative comes relatively easily. It comes. So this can also be learned, right? So we have now we have u is equal to minus 1 by 4 mu. Actually, it is better to write the minus sign along with 1 by 4 mu minus dp by d is set into r squared minus r squared. This indicates that a negative pressure drop would give us a positive uz. Positive uz means the flow is in this direction. So the flow will be in this actually in the positive direction of z, that is in this direction only when dp by dz is negative. If dp by dz is positive, the flow will be in this direction, opposite direction. If dp by dz is equal to 0, there is no flow. So the dp by dz is the magnitude of the dp by dz controls the value of uz. So it could be 0, it could be positive, it could be negative, and the magnitude depends mainly on this parameter dp by dz, which is the pressure gradient or the driving force for the flow. Now let us find out what is the average velocity. What is the average velocity or the velocity, uniform velocity at the inlet? For that, the continuity equation you can apply. So let us find out the discharge. Discharge at any point will be equal to 0. It will be equal to constant. Discharge at any point. So to find out discharge, what we do is, so we have let us calculate some radius. Take one more circle ring kind of thing. And the ring kind of thing. Okay, let us assume that this is a ring of a ring. That this is a ring. This is at certain radius. This is at certain radius r, having an annular ring at radius r and having the radial gap dr, and you have seen that this uz r is the velocity uniform within the gap dr. So uz into that area of the annular passage, uz into area of the annular passage is 2 pi r into dr. 2 pi r into dr gives the volume flow rate through that small annular gap, and the summation over all annular gaps from the r equal to 0 to r is equal to r, that gives T. So we have so these things are constant. 1 by 4 mu minus dp by dz into there's a 2 pi is also constant, so there's an r remaining. So integral 0 to r squared r minus r cube dr. This is a discharge. So 2 pi by 4 mu minus dp by dz, and this integration is r squared by 2 minus r raised to 4 by 4, r raised to 4 by 4, and that from 0 to r, it becomes pi by 2 mu minus dt by dz, and this is r squared into capital R squared by 2 minus r raised 4 by 4. And pi by 2 minus dt by dz into this is r raised to 4 by 2, this is r raised to 4 by 4. That becomes r raised to 4 by 4. So pi by 8 mu r raised to 4. So at the inlet, we have the total area cross section. Has an average velocity u bar. So the inlet discharge is this much, where u bar is average velocity, pi by 8 mu r raised to 4 into minus dt by dz. This gives this cancels 1 r square will go, u bar is equal to r squared by 8 mu into minus dt by dz. R squared by 8 mu into minus dt by dz as a u bar. So okay, the average velocity is like this. The average velocity is like this. Now, okay, this is about average velocity. We have got this particular equation, that is a Hagen-Poiseuille equation for the variation of actual variation of actual component velocity, and this is also Hagen-Poiseuille equation for discharge, discharge as a function of dp by dz. So when dp by dz is equal to 0, there is no discharge. And the discharge also depends upon the viscosity of the fluid and the radius of the pipe. The larger radius of the pipe will have a larger flow rate. So those are convincing observations. So next we'll see the wall shear. So wall shear stress, what is wall shear stress? Wall shear stress tau W is equal to mu into du by dr at the radius of the pipe. R is equal to R. So duz by dr. So what is duz by dr? Duz by dr is mu into 1 by 4 mu is there. Then we have minus dp by dz is there. Then within that capital R squared becomes 0 minus small r squared becomes 2r, and this we have to substitute r is equal to capital R. So this is 1 by 4 minus dp by dz minus 2 into r. Actually, one more thing is that I want to write the wall shear as a positive value, but if you look at dou uz by dou r, if you look at dou z by dou r, the uz reduces with increase of r. Uz reduces with increase of r. With increase of r, uz reduces. So actually, duz by dr is negative. Dz by dr is negative. So, but I want to write the wall shears as a positive quantity. So, when I write that equation of toe wall, I'll write a minus. So that minus will come here. So that minus will make this minus and eliminate it. So we have this. So this is this can be further written as that is r by r is there, and then the 2 is there, minus dp by this. So minus dp by this. And also we can have a dp by dz written as 8 mu u bar by r squared with a negative sign. That is also possible. Then we shall write tau w in terms of average velocity. So if you write tau w in terms of average velocity, it becomes r by 2. The minus dp by dz becomes 8 mu u bar by r square. So this has become positive. So 1 r cancels. So this becomes 4 mu u bar by r. So tau w is 4 mu u bar by r. 4 mu u bar by r. And supposing I write tau w by half rho u bar squared. So this is a non-dimensionalization of wall shear stress. So we know that half into rho u bar squared is the inlet kinetic energy per inlet. This is inlet kinetic energy per unit volume. So net kinetic energy per unit volume. So this has the unit of Newton per meter square as that of tau w. So the wall shear stress as a fraction of inlet kinetic energy per unit volume. If you want to write that, so this becomes u bar square. So this 2 becomes here 8 mu u bar by, there's an r. There's a u bar, 1 u bar cancels. So this this is 4 yes, correct. That's correct. 8 mu, there's 8 mu. The R, I will write it as the diameter of the pipe. Okay, I will put the diameter as capital D because of capital. So D by 2 into rho. Okay, this mu by rho, I replace mu by rho as mu, so that it is somewhat simple. And this comes 8 into 16 by d u bar by nu. So this d u bar by nu is a dimensionless quantity. So which is called, okay, so numerator I am having this inertia force and okay, something simplification of the inertia force and viscous force. That simplification also will get into this dimensionless group. So this is popularly called this Reynolds number. So what is Reynolds number? We define as d u bar by nu. So we use the characteristic dimension diameter of the pipe as the characteristic dimension, average velocity as the characteristic velocity, and kinetic, that is kinematic viscosity. So that gives the dimensionless group, which is equal to Reynolds number. So this is a dimensionless quantity. That is this is called the coefficient of skin friction, CF. So that is 16 by R. So the coefficient of skin friction is 16 by R. That is a coefficient of friction. Which is also called Darcy's coefficient of friction. Darcy's coefficient for a pipe flow. So this is the common name is the skin friction coefficient. So as in the pipe flow, we get this, and this is also called the Darcy's coefficient of friction. Now let us write an equation for dp by dz in terms of, we have this equation dp by dz. This let us take again. to write the pressure difference or pressure head loss, an expression for the head loss, pressure head loss due to friction. So that if you take dp by dz is equal to dp by dz is equal to 8 mu u bar by r squared. So actually, okay, what we want to do is that, okay, this u bar is a constant, this u bar is a constant, so this u bar is a constant, mu is a constant, this is dp by dz a constant, dp by dz is a constant, as far as the Hagen-Poiseuille flow is concerned, dp by dz, the developed flow, dp by dz is a constant. So we can find out the pressure difference over a certain length of pipe flow. Suppose we have a certain length of pipe flow, L, L. So there is a pressure P1 here, there's a pressure P2 here, this underlying axis is like this. So we can have Vp is equal to minus 8 mu u bar by r squared dz, and integrating this everything is constant, so between 1 and 2, and the length will be 0 to L, you get P2 minus P1. P2 minus P1 is equal to minus 8 mu bar by r squared, and this is z, and we get L, and that can be taken to this side as this. This is the pressure. This is the pressure drop. Pressure drop. If I want to write pressure drop, I have to write P1 minus P2. The pressure drop P1 minus P2 by L is equal to 8 mu u bar by r squared. And okay. Okay, this L I will retain it here itself. L I will retain it here itself. And I want something like P1 minus P2 by rho g. So if I divide by rho g, it is the head loss. This is called the head loss due to friction. Head loss due to friction. So if I have a rho g division, so that is normally written as HL. HL is equal to 8 mu u bar by r squared L by rho g. And supposing that I want to write it in terms of, actually what is velocity? The velocity head. The velocity head is the u squared by 2g. U squared by, this is a head. So velocity head is u squared by 2g. So let me have a u bar here, and let me have a 2 over here, so that I will have a 2 here. Sorry. Okay. So okay, I should have a 2 here also. So that makes a 16 mu by r squared. There is a rho is there. There is an L here. This is u bar squared by 2. U bar squared by 2 and g. 2g. So the head loss is in terms of velocity head, something else will get. So HL I can write it as, so actually it's only rewriting of these equations. Just we are rewriting the equations. So HL is equal to 16 mu L by r squared rho. Actually mu by rho, let me write it as nu, kinematic viscosity, that is better. So let me rewrite this r squared into d into d. R is d by 2, 4. D into d is 4, so that 4 comes here. So these things, sorry, there's a u bar. When I have a multiplication of u bar here, U bar here, there should be a U bar division also. You are in this for this U bar there should be a U bar here. So there is a so there is something. This is 4 into. So what I want to say is that there is a U bar over here. So there is a U bar over here. So there is a U bar over here. So du bar by du bar by nu, you can write it as a Reynolds number. So this will become 64 EL by d into Reynolds number into u bar squared by 2. So the head loss due to friction in pipe can be written as 64 by 64 by RE, 64 by RE, L U bar squared by 2GD, this kind of form. Okay, this 64 by RE is called as friction factor. If we take this as friction factor, 64 by R. So that is the popular equation Fl U bar squared by 2GD. So that we get from Hagen-Poiseuille velocity equation. So Fl is squared by 2. And also we know that the CF is equal to 16 by R. So that way we can write this in terms of CF also. That is Darcy's coefficient of friction. In that case, we have to multiply 4 CF. So 4 CF will match it. So it is 4 CF L U bar squared by 2 UB also. So we have this HL, loss due to friction is equal to um, 4 CF L U squared U bar squared by 2 G or F L U bar squared by 2 GD and CF is 16 by Reynolds number and F is 64 by Reynolds. So this is called Darcy's coefficient of friction or skin friction coefficient. Darcy's coefficient of friction or skin friction coefficient, and this is called the friction factor. So this end this lecture.